So in the last question of the most recent homework, the scaling that we did at the end of the last video lecture is already done for you. So it looks something like this. And as mentioned, if you wanted to know the proportion of values between 110 and 109, for example, whenever you have a scaled histogram, that is just an area calculation. So that would be calculating the area of this bar, which in this case, it looks like its width is 10 times its height, which is like 0.023. I also wanted to mention another thing. I kind of did it rather quickly on the homework, but in addition to scaling the heights of the histogram, I also had scaled these values on the y-axis. So what does that mean? I took the number 18 and I got 0.03 out of it. And the way that I did that is I used this formula and I plugged in 18, right? And that was just 18 divided by 60 over 10, which is how I got each of the values on the y-axis here. I wanted to mention that because I feel like it wasn't that clear on the most recent video lecture. So before I move forward, any questions on this?
I have a question.
Okay.
Are we going, like, I guess it's not that hard now that I'm thinking about this question to do, but are we going to be expected to, like, memorize how to use Excel and, like, how to input graphs and then, like all that stuff? Or are you going to provide, like, direction, I guess?
So I do provide direction in the sense of the lecture videos.
Yeah.
I mean, to get to your question, memorization is useful in the sense that if it's something you do a lot, right, you don't have to go and hunt for how to do it.
Yeah, exactly.
That being said, I'm not, all the tests and the quizzes in this class, you're allowed to use your notes. So directly to answer your question, no, you don't have to memorize it. You should probably write it down somewhere so you can access it. And if you don't want to be under too much of a time crunch for the quizzes and the exam, then having at least an intuition on what needs to be done will likely be helpful.
Yeah, I guess I'm just asking, like, is it going to be, like, I know that sometimes, like, in the homework and stuff, you provided, like, a little direction on how to do it on Excel. Like, is there going to be that?
You might have to refer back to previous homework. I won't always give you the explicit instructions.
Okay, sounds good.
All right. Any other questions?
I had a question.
Okay.
I was wondering if the midterms would be like multiple choice the way the homework is, or on paper and then we scan it on.
The midterms are also going to be on WebAssign, so you don't need to scan it. You don't need to put it on paper. But I will tell you now, they will not be multiple choice. Any other questions?
I had a question. So in one of the video supplements that you gave, I don't remember what exactly the example was, but the bin was 10 and the range was like 80 to 89, for example.
Yes.
And on the homework, I don't remember exactly what the range was, but I thought it was 21.
Was it inclusive or exclusive? That's actually an excellent point. Yes, so on the example that I gave in lecture, I used inclusive bins. So that means the top and the bottom range here were both included for this particular bin. And that's actually that's a very astute point. It seems on the homework, I then used, and everybody had a different input code, so this was different for everybody else, but it was something along what lines of like 80, 90, 100, 110, right?
Yep.
And for future reference, just as a convention for this class, I would say view these as, if you wanted to view this as inclusive, view this as 80 to 89. So that it's inclusive for the bottom point, but exclusive for the top point. You can also write that as a interval like this.
So that would still be 10?
Yes, both of these express, well, in this, I guess I'm giving another example. In the homework, it was 20. I'm giving another example of a 10. But no, I'm writing out the whole range in this example, whereas this example, we would write these histograms in between the upper and lower cutoffs. And yes, they still involve a bin width of 10, but as Olivia astutely pointed out, is the point 90 included in this bin or this bin? And I'm telling you, just always assume that it's included in the upper bin. All right?
So just the lower point would be included, and
Yes,
everything at the
yes.
top isn't.
And
So
the
that's
top one is included in the next bin. That's an excellent question. And it's something that perhaps you should ask in the future when people make histograms for you. I am setting forth this convention for our class.
thank you.
Of course. Any other questions?
Could we go over what confounding variables are again one more time?
Of course. So the idea of confounding variables is whenever we do an observational study, we are usually interested in this idea of explanatory and response. So our example was percent of sunscreen usage on the x-axis. And on the y-axis, we had skin cancer occurrences. And if we were to draw this scatter plot, we talked about there was a positive association, right? So what we would like to say as researchers, and in fact, what is sort of the sexy thing to say whenever you're doing statistics is, well, hey, percent of sunscreen causes skin cancer. And the idea of a confounding variable is sort of the reasoning as to why we cannot say this. If we observe this, we cannot say this. And the reason that is because there may be something that causes both of them. So we gave the example of being out in the sun a lot. This is a variable that may cause an increase in both of these things. So saying that these two things cause each other wouldn't really be accurate. They are actually just going both up at the same time because of some other variable that causes changes in both of them. And we would call this variable a confounding variable.
All right, thank you. That makes a lot more sense.
Sure. Any other questions about this? Awesome. I appreciate it. Questions make class a lot more fun. So I appreciate this from all of you. Thank you. All right, so I'm going to jump back up here for a second. And I'm going to name our section. We are going to describe distributions with numbers. And before we can start describing our distributions, we should probably say what a distribution is. So the distribution of a variable tells us what values it takes and how often it takes them. All right. So a histogram is an example of something we can use to visualize the distribution. So what did I just say? A distribution tells us what values a variable takes and how often it takes them. So in this case, we had IQ scores. And it would appear that our IQ scores took values in each of these bins, right? We saw values between 80 and 149. And by binning them, we talked about how often each of these different segments of possible values occurred, what values it took, and how often it took them. It took values in this range a lot more than it took values in other ranges, right? These are sort of, I'm trying to give you qualitative ideas of what a distribution is and how we would think about distinguishing one distribution from another. To motivate this a little bit more, I actually, excuse me. So a histogram is how we're going to think about it. And there are three main ideas. We are interested in the center, the spread, and the shape. And we're going to spend some time this lecture talking about what each of these means and why it's an interesting thing to talk about when we're thinking about distributions. All right. So before I go on to describing these two things, I have a slight poll, hopefully to kind of wrap up our talks about distributions. So talking about our histogram that we made, this histogram right here, the scaled histogram that we made in our last video lecture, I actually have a poll for us to take. Aren't these fun? I think they're fun. So, can you all see it? Nice. All right. I'll give us a bit of time to take it. All right, let's go ahead and end this. We've had about 45 seconds. And can somebody tell me how we did?
80% said 1, 10% said 1.05, 5% 0.97, 5% 0.5. Nobody said negative 0.7.
That's good. Negative 0.7 was the least correct one. So if there could be a least correct one, it was that one. So very good. And very good to all of you in the majority, since 1 is the correct answer. Each of the areas under the curve here, they give us a proportion of values, and that is a proportion of the total. So if we added up all of the proportions for all possible values that add up to the total anyway, we're basically asking what proportion of values in the total are of the total are in the total, which is just 1. They should add up to 100%. And this is actually kind of a crucial idea, is that the total area under the histogram is equal to 1. We're about to make the jump to something called density curves. And in that case, the total area under the curve is also 1, but we'll get to that in a second. First, we're going to talk about how to think about distributions. So the first one was center. And the center is an idea of like, what's the average, what's the most common value of a distribution? And we have 3 ways of thinking about it. First is the sample mean. Which I hope all of you have seen an average calculation in some form or another in your previous classes or just in life. Our shorthand for this is X bar, and it is really just the average of all the values that we've observed. And I'm going to take this opportunity to remind us of our summation notation. So this is Greek sigma, right? And it's not sigma times xi. You read this as the sum of all of the x values. So that shorthand, I'll write it out what it actually is. It's like saying x1 plus x2 all the way to plus xn, assuming we have n observations, dividing by the number of observations. All right? The next one we have is the median. And the median is the middle value or 50th percentile that we'd get by ordering the data from least to greatest. So if you were to order your data and just look at whatever value is in the smack dab in the middle, that would be your median. The third is the mode. This is just the value that shows up the most common observation. So I'm not going into explicit examples with these because this is actually the topic of our next video lecture. I'm going to take some data and I'm going to explicitly show us how to calculate everything that we're talking about today. So if you don't immediately understand, definitely go through the video lecture slowly to try to get an idea of how you would calculate these, because we do need to know how to do it. I'm also, however, in the video lecture, I'm also show you how to calculate all of these in Excel. So you should know how to calculate them yourself, but I will also show you how to get Excel to just do it for you. One of the joys of the computer age. All right, spread is our next value. So those were all ideas of what is the center of the distribution. Now we're going to talk about what the spread of it is. And I want to start with a little bit of an example, or a photo, I should say. So we're about to talk about these things called density curves, which are just continuous representations of our histograms. But imagine these are actually, I'm sorry, this is the best photo I had. They're not actually histograms, but imagine that they were, right? So that each of these boxes look like that. Right, and this one's also a histogram. It's just a fatter histogram. Sorry. So note, for each of these distributions, the center is the same. Both their average, I believe their mode, their average, and their medians are all the same. However, they are very different distributions, right? We wouldn't say these distributions are very alike at all. They just have the same idea of center. One of them is very spread out. It's kind of squished down and spread out, and the other one is really, really squished in and very, very tall. And we would say that although these two have the same center, they have very different spreads of value. And the idea of spread is how far away from the center is every single value. This blue distribution has a lot of values that are very far away from the center, whereas this red distribution, most of the values are right in near the center. All right? So I'm actually going to say it's the idea of how far from the center is everyone. And we have two ways of calculating this. So we have three ways to calculate center, to think about center. And now we have two ways to calculate spread and to think about spread. And the first is likely the most common, which is sample variance and standard deviation. So sample variance. The shorthand for this is S squared. And this calculation, if anything makes you queasy today, this one might do it. Oh wait, I have another thing I might show you that might make you more queasy, but we'll see. It's this. So it's the sum. Remember, this is summation notation. It's not sigma times whatever is right next to sigma. So it is the sum of every single value's squared deviation from the mean divided by one, the number of observations minus one. So to write it out a little bit more, if you're uncomfortable with summation notation, which by the way, please try to become comfortable with summation notation because I will use it in the future. They are the differences between each observation and the average value squared, and then added them all up and divide by n minus 1. So it's kind of like you're taking every single value's distance from the center. You're squaring it, sure, but then you're kind of averaging those squares. So it's kind of like, it's not exactly this, and there's a reason it's not exactly this, which we'll get to in the future. But you can think about it as saying, what is the average distance from the center? Is a good way to think about standard deviation and variance. And just to be explicit, the sample standard deviation is just equal to the square root of the sample mean, of the sample variance, excuse me. Which is just the square root of s squared, which is the square root of this friend of ours. Okay, so knowing what we know about the sample variance and sample standard deviation, can anyone wager a guess as to which of these two curves slash histograms, the red or the blue, has a larger standard deviation?
Blue.
Blue?
Blue.
Nice, you are correct. The blue is much more spread out. The distance of all of the values from the center point is much larger, so we would expect this average of the distance from the center to be larger for the blue than for the red. All right? So it's a numerical representation of the spread. The next one we're going to talk about, and again, the video lecture is going to walk you through how to calculate the sample variance. Next one we're going to talk about is the interquartile range. Commonly known as just the IQR. So let Q1 be the 25th percentile of the data. So if you were to line up your data from least to greatest, cut it in half, that the median is at the half. Now just look at the first half and cut that in half. That midway point is going to be the 25th percentile. And similarly, we want Q3 to be the 75th percentile. And again, in the case of 75th, we cut it in half, but now we look at the top half and we cut that one in half, and that's going to be the 75th percentile. Again, this is something we're going to go over more explicitly in the video lecture. The IQR then is simply Q3 minus Q1. Boom. third thing we want to talk about is shape. Oh, excuse me, I'm jumping the gun. So these are our two ideas of spread. The next thing we want to talk about is indeed shape. I just want to make sure I put the right thing on here. Yeah, that should be fine. Okay. Shape. And again, I'm going to start with a picture. So remember last time we had those two histograms that had the same center but different spreads?
Mm-hmm.
Well, this time I want to show us, I'm going to do this on a new page. Oh, goodness. Oh, gosh. Oh, my soul. Come on. So each of these histograms on this picture here all have the same center. They're, I guess in this case, we're defining center to be the mean. So they have the same mean, and they have the same spread, which in this case, we're going to define spread as the standard deviation. So all of these have the same standard deviation if you went and calculated, and they all have the same center. But you'll note they're all very different histograms. So that kind of begs, do we have a third way to describe distributions? Because just knowing the center and the spread doesn't really tell you everything about how the distribution is. And the answer is yes, we have descriptive ways of talking about the shape of the distribution. So actually the first two are what we would call symmetric, but I'm gonna use this one to motivate because the first one is a very weird case. So we would call this symmetric. And I think I've mentioned this already in one of the video lecture. But basically, if I were to draw a line down the center and then fold it in half, it would approximately line up, right? And you'll note we can do this as well with this one. So that's why I would call this one symmetric as well. This one is what we would call right skewed. And right skewed means is in the case where we have a very long tail and that tail is pointing to the right. So in contrast, we can also talk about left skewed, which is the only other one we're really going to talk about. And that is the case. I'm sorry it wasn't it wasn't really on the picture that I found. I just told myself, well, I guess I'm drawing a left skewed myself. So this would be the example of left skewed. It's when, in contrast to right skewed, there is a long tail and it is pointing to the left. So I always think this is kind of fun, but no one has really told me that they also think it's fun, so please shout out if you do. The way I remember it, I always have, because, you know, remembering which one's left skewed and which one's right skewed is just one of those things that's always shows up on some sort of question and you always get them confused. I don't know. If you're anything like me, I always get them flipped up. So the way I remember it is I always draw a little, I always draw a little monster, and the direction that the monster's tail is pointing is the direction that is the correct direction. So this is right skewed because his tail with an arrow at the end is pointing to the right. It's allowed to just be me, but this is how every single time I draw the monster. All right, so here I have a poll, I believe. So let's do it. All right, can we see it? Nice. So which of these is a correct interpretation of right skewed? So we're looking at the third buddy right here. All right, so it's been about 50 seconds. I'm going to end the poll. And will somebody tell me the results?
It was 48% for most values in the lower range, 48% for most values in the upper, and then 4% for low and high values.
Oh, so we're tied?
Mm-hmm.
Ah, that's kind of fun. Well, I will be the tie-breaking vote. I would say in the case of right skewed, most of the values actually show up in the lower range. So kudos to all of you. The reason this is, so remember whenever we were talking about density under the curve, that refers to the proportion of values in that area, right? So in the case of the right skewed, we're seeing a lot more density on the left side, which is where the lower values are. However, we are also seeing not a larger amount of density, but we're seeing the presence of high outliers. So we're seeing a bunch of values in the extreme of the high, but the density itself is in the low, is how you should read this. Make sense?
So you don't really look beyond that last. So in that particular plot where you have that last bin at about negative 1.5, if you don't see values, there's no values to the left of that.
So for this third histogram, you're right. There doesn't appear to be any observations beneath
Right.
negative 1.5.
So we assess the shape based on where we have bins, essentially.
Yes, exactly. Often, I guess we may come to a point where, you might approximate this, which we're actually about to talk to with a line, and maybe you'll have like a really tiny amount of density that goes on for infinity, but usually that density becomes pretty inconsequential. We're more interested at where the majority of the probability mass is, which is in this area right here. Yeah, excellent question. Any other? Yeah?
Yeah, it's the upper range with very
So there's more mass on the lower range of values. That's why we see this bump right here, right? The thing that happens in the upper range is we have a few values that could potentially be outliers. So we've noticed a few values in the way upper range, right? Not that many, but they're more extreme than, they're kind of like more extreme from zero, I guess, or more extreme from the center is, I guess, what you could think of it. You could think of it that way.
Okay.
Yeah, so more mass on the lower side, but perhaps with outliers. The outliers is what gives us that tail, that sort of thin tail. All right? So this is great. It kind of motivates the next thing we want to talk about, which is density curves. All right. We'll start with a definition. I wonder what it's going to be. A density curve is a mathematical model of a distribution. And we have a picture. This one. So note these histograms. So say we took a very large sample, and it would appear we took samples of heights. Oh, I should have used one of our class things on this. I didn't. Let's say height of giraffes in centimeters. I think giraffes are way taller than this. Height of rats. Dogs. We'll say dogs. Heights of dogs in centimeters. Note the bin width here looks like it's about, what is it, 10? Yeah, this one looks like it's about 10. This one maybe is 2, 4, maybe like 4, maybe this one's 2, and this one looks like 1, right? The bin width is getting smaller and smaller, and as it gets smaller, as you would expect, we get finer and finer rectangles. And what I want to motivate here is as our bin width gets finer and finer, so we could even go less than 1, we could go 0.5, we could do 0.1, and so on and so forth. As it gets finer, it looks more and more like we might be able to draw a smooth line. Oh, that was a terrible. Let's zoom in. Like we might be able to draw a smooth line that would express this distribution. Right? Instead of just looking at the little jagged side, what if we just had a distribution that was a smooth line? And that's a pretty big idea in statistics. If we ever observe data that looks like it would be well approximated by a density curve, we often do that. So if we observed a histogram that looks something like this, we might, instead of doing all of our calculations on the histogram, do our calculations on a density curve that looks like this, like just a rectangle, which actually we call the uniform distribution. Right? So, you know, math is often interested in modeling things. We observed this sort of random phenomenon. We noticed that a smooth line fit it very well, so we decided to just use the smooth line and then to do all our calculations on this thing instead. And this is, density curves are kind of one of the bigger, or it's one of the first theoretical jumps we need to make in this class. We need to say, we can think about them as histograms that got finer and finer until they just became a smooth line. That's one way to think about a density curve. Or we can think about them as just like, oh, well, our data kind of looked in a certain shape, so we just kind of drew that shape and used that shape. Okay? So I'm going to move us into thinking about doing a bit of an example with this and trying to think about the implications of a density. The first thing I want to talk about is that there are some well-known density curves that come up a lot. They come up a lot because of certain random phenomenon in the real world, or just the way data seem to be shaped based on the experiences of researchers. So we give them names. And I have a few little examples of that. The one that we just showed, the one density curve that just looks like a rectangle, is called the uniform. There's another one. This one doesn't come up as much, but you may see a question on it in the future. He, is called the triangle distribution. There's one that looks like this, kind of goopy, called the Erlang, which also might show up in the future. And then there is a very well-known one that I hope all of you have each at least seen peripherally, which is, oh goodness, that's not that great, called the normal distribution, otherwise known as the bell curve, right? So these are all very well-known distributions. And there are many more besides this, and they come in all sorts of shapes and sizes, but I want to mention a few things about them. Like our histograms, the area under the curve is always 1. So in the uniform case, it might be easy, right? We just need to find the area of this box. So if I gave you the y-axis and I gave you what the numbers were in the x-axis, if you were to calculate the area under this curve, it would be equal to 1. Just like in the case with our scaled histograms. Same thing with the triangle. Same thing actually with the normal and the Erlang, but you'll note that finding the area under the curve in these two cases is a little trickier. We can't just use base times height, right? The line's all curvy, but we'll talk about that in a second. So the area under them is always equal to 1, and they come in many shapes. Also just like our scaled histogram, finding proportions is the same thing as calculating the area under the curve. And I have an example for us to do. I have this friend who's a brilliant mathematician, and she's also an excellent artist. And oh my gosh, some people just have it all.
You're not doing a bad job.
Thanks. I must assure you, though, I pale in comparison.
Far better than what I would do.
All right, so this is an example of a uniform distribution, right? We have our height right here. The height of the curve is 0.1, and it spans between the values of 10 and 20. With this uniform distribution, I have a poll for all of you. It is our second to last poll in this class. I hope you all like these polls as much as I do, but I must tell you, I'm gonna do them either way. Okay, launching the poll. Can we see it? Nice. I'll give you a bit of time. And also, here, I'll zoom in, make it easier. All right, about 5 more seconds. Very nice. So what proportion of values would we expect to observe between 10 and 14? So think right at the beginning here. The proportion of values we would expect to observe is just the proportion of values in our sample that we observed between 10 and 14. So I'm going to share the results here. Can somebody tell me how we did?
93% at 0.4, and then 3% each at 1 and 0.2 respectively, and 0% at 10%.
Hey, very nice, all of you. You got it. I will go through it briefly. We want to know the area of the curve between 10 and 14. That is specifically, we want to know the proportion of values between 10 and 14 because it is a quality of density curves that is equal to the area under the curve right here, which is this box. Thus, which, as I'm sure you all did, you take the height, 0.1, times the span, which is just 14 minus 10, which is 0.1 times 4, or 0.4. Very nice. So just like our scaled histogram, area under the curve calculations gives us the proportion of values that we observed between that area, between those proportion of values that we observed in that range. I have one more question, and I will tell you now, I got a crazy split in my last class. It was very exciting. I'm interested to see how you all do on this one. All right, what proportion of values do we expect to be equal to 15? Oh, my goodness. I erased my, excuse me. I did so accidentally, I assure you. All right. It's about 55 seconds, so I'll go ahead and end the poll. And will somebody tell me how we did?
50% at 0.001, 18% for 0, 9% for 1, 23% for 0.5.
Very nice. So actually, the 9% of this class take the cake, which is very fun. It was a tricky question. So we want to know the percentage or the proportion of values that we observed at 15, or what we would expect, our best guess at the proportion of values, which is just going to be the area of the curve at 15. Now that's very tricky, because what that is right here. It is literally just this line. So what is the area of that line? That is, well, 0.1 is the height times the width of the line, which is actually just 0. It is 15 minus 15, which is equal to 0.1 times 0, or 0. This is all to say that a single point on a density curve, this is a continuous approximation of our scaled histogram, or of whatever data we've observed. A single point on a density curve is given a proportion of 0. We cannot actually express probability for a single numeric value when it comes to these curves. And this is a very important point. I hope we eventually grow to understand the nuances of what this means. But know that if you want to do a proportion or a probability calculation with these density curves, you need to be doing it on a range of values. If you ever try to do it on a single value, it'll be 0 automatically. And I will mention that is a very good test question to see if you remember. So something to keep in mind. Any questions on this?
Yeah.
All right. So density curves work the same way. Area under the curve is equal to the proportion of values that we observe in that area. The next thing I want to do with the time we have left is I want to do a soft introduction to the most famous of the density curves, the normal distribution. So this is often referred to as well as the bell curve. And I hope you all get the joke. It's because it kind of looks like a bell. In fact, I was saying at my last in my last class, if I wanted to draw it as a bell, I should also put this little crack, because I'm from PA and the Liberty Bell has a crack in it, so ha ha ha. You didn't know Liberty Bell is in Philadelphia. That is where it is. So this is the bell curve, called that way for its bell shape. And I want to show you something kind of interesting, is that calling something a normal curve doesn't really tell us everything about that curve. And what I mean by this is I'm actually going to show you a bunch of pictures of a bunch of different density curves. I mean, normal curves. So there are 6 curves here, right? We have 3 curves here, 3 curves here, and 3 curves here. And every single one of them is considered a normal distribution. So that is to say that the normal can show up in many shapes and sizes, but it's always going to be shaped sort of like this bell. Now, the distinguishing factors between these 3 are that they are all the same curve, but they're shifted, right? Now, that is to say that their centers are all different, right? If I were to draw where the center is on each of these curves, it's at a different place for each of them, correct? So these are 3 normal curves that all have different centers. Over here, we have 3 density curves that all have different spreads. Remember when you have, in this case, I'm referring to standard deviation as my spread. And remember when you have a very wide curve that's kind of squished down and there's really thick tails, that has a large standard deviation, and when it's squished together and it's really tall, it has a very small standard deviation. So these are all the same curves, all with the same center actually, but different standard deviations. So I'm going to hit you with a fact about normal curves, and I hope we can motivate it more in the future. If you don't quite understand this sentence, you will be given more space to try to understand it, I assure you. But if you know the mean, which we're going to call mu, and the standard deviation, which we're going to call sigma, then you know everything about a normal curve. So these curves were distinguished from each other based on their centers, which in this case is mu. We're going to call it mu, which is a Greek symbol, and their spreads, which is sigma, another Greek symbol. And what I'm telling you, and I hope to motivate it more in the future, is that if you know where a normal curve center is and you know what its spread is, then you can draw it. Then you immediately know everything about it. There are no other distinguishing factors of a normal curve. So in a way, calling it normal is sort of an expression of shape, and the other 2 things we need to know are center and spread, right? The 3 things we want to know about distributions. So I'm going to end this lecture with a little bit of a nod to your algebra backgrounds, which I hope you all have. I never check. People never really check the prereqs, so I assume you all have seen this picture. If I were to draw this line right here, I can also express this line as an equation. It's actually just the line y equals x, right? Similarly, if I were to draw this line, otherwise known as the normal distribution, it is also a line, and it also has a formula, which I'm going to give you. Again, you're not expected to really memorize it, but I can't really take you through a statistics class without at least writing it down. This is the equation of that line. In fact, maybe I should have drawn this as red. This line, just like how this line over here had an equation, this line has an equation here, and it's this really complicated beast. So, I mean, it's in your notes. Everything we do in this class is open notes, so at least now you have it written down somewhere. No, if we wanted, so remember when we were working with our normal distribution, we often wanted to talk about area under the curve. Well, note that it is a very difficult thing here when the line is very wavy to calculate explicitly what the area under the curve is. There is a way to do it, and please do not sign off this video until after I explain this to you, because I'm not expecting you to be able to do this. I'm merely putting this in here because a lot of you mentioned your calculus backgrounds, and ultimately how we would calculate the area under this curve is with the following integral. So if I wanted to know the area up until the point, I don't know, maybe this is -5. That would be the integral from -infinity to -5 of your normal density. So that's why this equation can be good, because it ultimately gives us that area under the curve calculation that we've been doing a bunch, which is going to become super useful and important as we actually start working with testing conclusions and hypotheses. Yeah, so this is how you would calculate that area with this equation using the integral, for those of you who haven't experienced it in calculus. But this is all to say, and maybe some of you will be happy, maybe some of you will be sad, but I will never expect you to calculate this integral. In fact, it would require stuff beyond calculus 1. I don't even think you do this in calculus. You would be able to approximate this in calculus 2, but I don't think you learn any way to actually do a calculation of this until the 3rd level of calculus, which is definitely not a prerequisite for this class. Instead, we will use Excel. All right? So it is merely for your own edification that I bring this up. I may choose to ask you at some point a question or two about this equation itself, but I will never have you do this integral. All right? I believe that is the last thing I wanted to cover about the normal before I get too far ahead of myself. Are there any questions? All right. So the video lecture should be posted. I'm realizing now, here, I'm going to stop recording.